Let's continue our solution of problems in Siegel's biochemical calculations in page 93. We are going to be working now on problems 47. Siegel, number 47, and this can be found in page 93. This problem asks us to calculate the volume of 0.2 molar HCl, which volume of this would be required to titrate completely. In the part A of this problem, they ask 200 milliliters of 0.25 molar of isoelectric lysine. Let's leave this outside for a while while we solve this problem. So the first thing we have to do in a situation like that is to write the exact form so that we can think more clearly. So isoelectric lysine is the form that has a plus and a minus, so the charge is 0. So let's write this form here, which is H3Na plus CHCOO minus, and we are talking about the isoelectric lysine. So lysine is going to be CH3. All right, so that's isoelectric lysine because we have a negative charge in here, positive charge there, and it makes neutral. So if you are going to titrate this thing, and we are going to add hydrochloride to titrate that with sodium of HCl, then what we're going to do is that we're going to need to add 1 molar of protons to be able to protonate that completely becomes the fully protonate form of isoleucine. So in other words, what we have here is that for 1 mole of isoelectric lysine, you need 1 mole of HCl. So the relationship is very clear now, and the problem becomes very simple. So we have the number of moles of isoelectric lysine, that we have is going to be equals to the molarity that we have for isoleucine, which is 0.25, multiplied by the volume that we have for that one, which is 0.2 molar. So this don't need the calculator this time, 0.05 mole, right, of isoelectric lysine. So therefore, we need the same number of moles of HCl to be able to titrate completely that solution. All right, so now we know how much we have of the solution of HCl, which is 0.2 molar HCl, so we can calculate the volume. The volume, as we did many times, is going to be the number of moles divided by the molecular weight. Number of moles divided by molecular weight. The number of moles that we need here, not molecular weight, but the molarity, 0.05 divided by the molarity of that solution, which is 0.2. So this would give 0.25 liters or 250 milliliters of HCl 0.2 molar to completely titrate that solution of isoleucine. So let's move it to another page here so that we can, in the sequence, also do the part B of this problem. So the part B of this problem is asked again the volume of HCl, but this time the volume of HCl to titrate 375. Let's write here to the sequence that this is 47B. So the volume is to calculate the titration of 375 milliliters of 0.25 molar, and this time is isoelectric glutamic acid. So the isoelectric form of glutamic acid is going to be H3Na plus CH COO minus, and CH2, CH2, COOH, right? Because it's isoelectric form, and we know that the first proton to come off is the one from the carboxylic group, not from the side chain, but from here, right? So that's going to be negative, and this charge here is positive, so that's the isoelectric glutamic acid. Now we know that in order to titrate that completely, we have to add 1 mole equivalent of HCl to protonate this carboxylic group. So our relationship now is 1 mole of isoelectric, 1 mole of isoelectric glutamic acid, and 1 mole of HCl, right? So the number of moles of isoelectric glutamic acid that we have is very simple to calculate. It's just the same thing as we did before. The molarity, which is 0.25, multiplied by the volume in liter, which is 0.375. This would be more accurate if they calculated at hand to avoid miscommunication here. So this is going to be 0.09375 moles. Okay, so this is going to be the same number of moles of HCl. So now to calculate the volume of HCl on the same principle as we did before, is going to be the number of moles, that is 0.0937. You could round this number here as well, divided by the molarity, in this case, a molarity of HCl, which is 0.2. So when you divide this by 0.2, you are going to get 0.68. Let's make it 0.847. Let's make an approximation here. 0.47 liter, or 470 milliliters of HCl to completely titrate this solution in part B. So the solution of isoelectric glutamic acid. Let's move on, change page again, and doing the sequencing here, the 47C. In the 47C, again, same thing, HCl, and the 0.2 molar, and there's 490 milliliters of 0.25 molar of isoelectric lysine. Now it's isoelectric lysine. Let's write this thing down here, 490 milliliters of 0.25 molar of isoelectric lysine. All right, so let's write the structure of lysine and then find out the isoelectric form. So what we have then for 0.25, 400 milliliters. So we starting here, isoelectric lysine is going to be H2N, CH, COO minus. And lysine is that long one, has 4 methylene groups, CH2, 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 NH3 plus. Right, if you want to know why did I find out that this is the isoelectric lysine with the charge in here and the charge in there, is because the side chain has a pKa higher than the pKa of the amino group. Okay, so let's remind ourselves here that the side chain has higher pKa. Remember from the table that we present in class and things like that. So in other words, the first proton that's coming off is coming off from here, and the second one is going to come from here. That's why I wrote NH2. And then the third one will be from the side chain. Since we have isoelectric, we have to have a plus and a minus to be isoelectric. So that's why we didn't go further to eliminate the third protons from the side chain. So now we know that this, in order to titrate this thing completely, we needed to have 1 mole of protons from HCl from here, and we need also another mole of proton from here. So this is a different relationship. This relationship now is 1 mole of isoelectric lysine is going to require 2 mole of HCl, right? It's a case by case, 2 mole of HCl. So now we calculated the number of moles of the amino acid that we have. So let's calculate the number of moles to make sure that we are on the same page. The amino acid lysine here, the isoelectric, we had 0.25 molarity, and the volume is 0.49. 0.25 times 0.49. This gives us 0.1225. That's the number of moles of lysine. Number of moles of lysine. Then the number of moles of HCl, is going to be twice as much that 1. So it's going to be 2 times 0.225, which in this case in here gives 0.245 moles. All right. So that's the number of moles. And how do you calculate the volume of HCl? Again, volume of HCl in liters is going to be the number of moles, which in this case is 0.245, divided by the molarity, which was 0.2, right? So we have here, again, going back to 1.225 liters. 1.225 liters. Let's double check all the calculation here so that we don't get any information wrong in the video. 0.245 and divided by 0.2. Yeah, that's exactly what we get. 1.225 liters, or in other words, the volume that we need of this HCl solution is 1,225 milliliters of this solution to titrate completely this solution of isoelectric lysine in the condition that was given in the problem. So this is part C of the problem. That's one less part of the problem, and that's part D. Yeah, that's the last one. Let's use that. Let's change gears here and move to the next part of the problem. All right, so the last part of the problem is with a solution of 125, and again this is part D, 125 milliliters of a solution 0.25 molar, and now the solution is a sodium salt of lysine. Now we know that lysine has to be negatively charged, right? Because we want the sodium salt, so that's going to be a negatively charged lysine. So how the lysine gets negatively charged is that we're going to have now the structure of lysine. The form that we're going to have is NH2 CHCOO minus. This proton was the protonate, and we have the 4-methylene group here. And now this is going to be deprotonated as well, because if this is deprotonate, we have charging here, no more charging here, no more charging there. So therefore, we have the lysine minus as required by the problem. In this problem, if you have lysine that's in the negative lysine minus, you are going to need one equivalent of protons protonate the carboxylic group. We are going to need one equivalent of protons for here, and finally we are going to need one equivalent of protons for here. So in another words, we are going to have 1 mole of sodium salt of lysine. It's going to require 3 moles of HCl, equivalent to 3 moles of HCl. Let's calculate the number of moles of lysine that we have in this problem, the number of mole of amino acid, that lysine in this particular case here. It was 0.25 times 0.125. 0.25 times 0.125 is 0.125. 0.0315315 moles. And then the number of moles of HCl that's going to be required is explained in here. The relationship is 3. So now we are going to need 3 times this amount, which is that much there. So multiply this thing by 3. We are going to get 0.09375. Let's rewrite that 0.09375 mole of HCl. And what's the volume that we need to deliver these many moles of HCl? We calculated that based on the relationship of molarity. The number of moles is going to be 0.0937, and the molarity of the solution of HCl is 0.22. So now we have this thing divided by 0.2. It's going to be 0.46875, and blah, blah, blah. We don't need that whole thing. Just make it 0.468, which is, again, this is an approximation, which is approximately 468 milliliters of this HCl solution to titrate completely this solution of the salt of lysine.